Welcome back, everyone. For the last talk of the day, we have Xinwen Zhu from Stanford University, and his title is p-adic Hyperbolicity of Shimura Varieties.
Thanks a lot for the invitation to speak in this wonderful conference. So the goal of this talk is trying to give you some flavor of the following theorem, which is recently proved joined with Abhishek, Oswal, and Shankar. Myself, which says the following: let AG is the moduli of a moduli space of principally pluralized abelian varieties with certain level, with let's see, ocean-free level. Namely, I want to have a fine moduli space. And AG star, it's minimal compactification, or some people call the Baily-Borel compactification. Okay, let F over QP, we'll always fix a prime P be a discrete valued non-Archimedean local field. And S over F is let's say smooth, actually, yeah, smooth rigid analytic variety. Then every analytic map F from the punctured unit disk MS to, let's say, an identification of this Shimura of this modular space. This is a modular space defined over Q. Okay, so I can take its base change to F and take its identification. Extends to an analytic map from, with the same notation, from the unit disk, I denote by delta, to the minimal compactification. So here, here is delta is just a unit disk. Delta cross is punctured unit disk. Okay, and by some kind of standard argument, which I'm gonna review in a minute, if S over F is an algebraic variety, and then every analytic map from the analytification of S to AG, analytification of AG is algebraic. Okay, so that's the theorem I'm gonna talk about, which talk about a little bit about the background and the idea of proof. So for I actually gave such talks several times already, from last year, but I think finally we could deal with this whole moduli space, not just the those with good reduction part of it. So that's going to be something I hope to discuss later, like some new stuff. But let's start with some background. So is the statement okay? Right. Okay, so start some back. So let's record this this type of question. Actually, this type of statement is a very classical thing. This is starting from this great Picard's theorem. Let's first talk about what happens over C. This type of statement has its root in classical complex analysis, which says that if you have a map from the punctured disk to this Riemann surface P1 minus 3 points, 0, 1, infinity, say analytic map. Okay, here this D star is like a disk over a complex number. It says the following: every such map, then every such map actually extends to a holomorphic map. I mean, this is of course holomorphic map from the disk to P1. So this is a statement of the great Picard's theorem. Usually it's stated if you have a holomorphic function on the punctured disk with essential singularity, then it admits one point of C. Okay, so here you basically, if you miss like 2 points in C, that means it must be meromorphic, which means it has to extend to a disk to P1. So that's a really, this is really this type of theorems kind of generalization of great Picard's theorem, and this result actually implies how to write it. This implies actually this types of corollary already is if S over S is an algebraic variety, then every holomorphic map from S to, let's see, P1 minus 3 points is algebraic. Okay, so it's defined by polynomial equations. So let me give you review, because I just review this type of argument once, not do it in the future. So how to do that? Basic idea is that let's see. S is a curve, some algebraic curve with several punctures. Okay, so it's an affine curve, and I'm given a holomorphic map from this to P minus 3 points. Then over each missing point, you can take a small puncture disk around the missing point, and because of the great Picard's theorem, it says that all the map actually extends across this missing point. Okay, so what you end up with, you get this compactified thing will actually map to P1. But now you are in a proper projective situation, you see. So if you have a holomorphic map from a complete curve to P1, it's going to be automatically an algebraic map. So this is Gaga. So this is by Gaga. So this is quite general. This kind of extension property implies algebraicity. It also works in this non-Archimedean situation. There's also non-Archimedean Gaga. So it's okay. So let me also, because the title is about the hyperbolicity, so let me also remind you some concept, another related statement actually can be deduced from this algebraic theorem. It says this is so-called the little bit curve, which says every holomorphic map from C to this P1 minus 0, 1 infinity is constant. Usual statement is if you have a entire function which means in 2.2 values, then it must be constant. You can formulate it in this way. And the way adversity implies this is you can look at if you have a such map, then you can adversity must rises from a map from A1 to P1 minus 3 points. You can also look at the F and also F composed with exponential map from C to C star and then composed with F, which supposed also to be algebraic. Then, but the exponential map has infinite fibers. A point has infinite pre-image. This can't happen for algebraic maps. So if both F and the F composed with exponential maps are algebraic, that means F must be constant map. So this is a little bit hard theorem. But the usual thing is, but this is also implied by this so-called the uniformization theorem, which is P1 minus 3 point is uniformized, or maybe say it's or its universal cover is uniformized by actually I should write let's see H upper half plane, which is also you can realize this biholomorphic to open unit disk. The reason is because any holomorphic, the reason the fourth statement implies the third is because if a holomorphic map from C to it, then it lifts to the universal cover. But then by Newell's theorem, you have a bounded holomorphic function must be a constant function. So that's and people usually call this is like this Riemann surface is hyperbolic. Complex algebraic curve, or more generally, Riemann surface is hyperbolic. It can be uniformized. Upper space. Okay, so in the one-dimensional over complex number, in the one-dimensional situation, actually you have four different type of statements. The last one actually is usually use the definition of the hyperbolicity of the Riemann surface, but it turns out all of them are like equivalent. So see, if you have a Riemann surface that can be uniformized by open unit disk, let's say compact Riemann surface of genus bigger than or equal to 2, then all other statements. Okay, so now let's move to the higher dimensional generalizations, still over complex numbers. Then the situation is actually much more complicated. Actually, there is really those notions are in general not known to be equivalent. In general, I think they're not really equivalent, but all these implications are still kind of there. But there's no, reverse implications. So, over higher dimensional. there are different notions of hyperbolicity. And for example, the most, maybe the simplest notion is the so-called the p-adic hyperbolicity, which is basically taking this property as a definition. A complex manifold is called a p-adic hyperbolic if any holomorphic map from C to it is constant, for example. But there are sort of another equivalent in general. But let's go to higher dimension, but consider the particular following situation. So let D be a Hermitian symmetric domain. Let's say non-compact. Which is as a real manifold, it's always can be written as a G mod K for some like G is some semi-simple Lie group and the K is maximal compact. So G is basically the group of holomorphic automorphisms, and this can also be it's always simply connected and can be realized as a bounded domain in some complex vector space. So it's kind of generalization of this upper half space. Example is, for example, D is just this upper half space, or maybe more generally, like what we're considering is the so-called Ziegel upper half space, classifying all G by G symmetric matrix with positive definite imaginary parts. Okay. So these are like can be realized as can be realized also simply connected, actually contractible. It can be realized as bounded domain. Some complex vector space. So now let me recall an important theorem of Baily-Borel and Borel. Which is this that gamma in G be a, let's say, some torsion free. Not torsion free, but let's say sufficiently small. Arithmetic subgroup. So those are actually G are actually certain can always realize there's a certain metric real point of certain matrix group. Then you can also take, for example, it's Z point and arithmetic subgroup is some subgroup commensurable those like you take Z point. Then the first thing is you can take this quotient when gamma is sufficiently small. This action of gamma on this Hermitian symmetric domain is actually free. So you take the quotient. It's a well-defined complex manifold a priori. So the first part is actually theorem. It's Baily-Borel. Which says that there exists a canonical compactification D star now gamma. So which makes this usually a singular but the compact complex analytic space, which then can be embedded into some projective space as a closed subset, closed analytic subspace. And this star is exactly what I want to see this minimum start there. So the general construction of this is a pretty difficult, complicated thing. But anyway, there is such thing. The second is actually due to Borel, which is kind of a analog of this Greek-Picard theory, this content, which says the following. By the way, so now this guy is actually, you know, it has an algebraic variety structure. Even just think about the complex manifold, it's actually broadly hyperbolic because it's uniformized by some bounded domain. So like this condition still holds. But then it's much more difficult to prove, to have the following thing is if you consider some punctured maps from punctured disk. So D cross A times delta star to the 8th power times delta B to this thing. Every such map, holomorphic map, of course, extends to a map from the poly disk to the minimum compactification, making the diagram commutative. Okay. So it's okay. Yes.
Does that characterize the?
Yes. So now, of course, as remark, just write it here. Remark is 1 plus 2 implies also imply there exists a unique algebraic structure. On this big gamma. Why? Well, part one already says there is an algebraic structure. But suppose there are two, then you just take the identity map as a holomorphic map from one algebraic structure to the other, and then the algebraic structure arising from one says that that map must be an algebraic map. Therefore, it must be the two algebraic structure must coincide the same thing. Okay, so this is a uniqueness also. And of course, the particular case also remark is we call that when gamma is a congruent subgroup. Want to attempt to define, then this is basically a component. It's a connected component of so-called Shimura variety. Shimura variety, and it can always be defined over some number field.
Explain the first remark again, because this compactification is singular, right?
The compactification is is singular. Yes, but the algebraicity map. I mean, I just use the algebraicity.
So you're not extending that.
No, can be defined over some number field. So now you arise a natural question. Suppose now already have an algebraic variety defined over a number field. over complex number, I have all these properties. Then how about I base change to some p-adic fields? I can ask the similar questions whether it has some similar properties. In fact, of course, you can directly ask this type of questions just directly for varieties of p-adic fields. But I mean, for me, it's always more interesting to to really study some algebraic variety over number of fields, but to understand its properties, both some complex method or p-adic method or something. So yeah, I should say the particular case when when D is what I use is Z equals upper half space, this HG mod gamma is just this AG with the proper label structure. So AG is the particular case. Okay. D mod gamma is just this AG modular principally pluralized abelian varieties with certain level. Okay, so so that's sort of some background of part of this story. Is there any questions? Yes.
In the statement about the existence of the algebraic structure, like what would be the algebraic structure in the case of the upper half plane, like when D is a unit disk and gamma is SL2Z or whatever? Like,
well, what is that's a sort of P1, right? But except there's some stack. The action is
oh, okay, yeah, sure. Sorry.
not free. It's just a
Yeah.
modular elliptic curves.
Yeah,
Yeah. Okay. So now we come back to. I hope I give you some background of the story, and now we come back to this analog of this theorem. So we basically, if you look at this theorem, then basically the sort of the analog of Borel's theorem in the case for AG, but of course then I should make a remark is I can erase here. Maybe just make a remark. Same statement for here only state for AG, but it same holds for Shimura varieties of so-called abelian type. Those Shimura varieties that are related somehow can be sort of more or less embedded into the modular space in AG. Also holds for like some other sub-varieties, like also like MG or something like that. Anything if it can be embedded into AG there. Okay. But actually I should figure it that the case of MG was actually previously proved by let me try to see whether I can find it. Yeah, this is actually proved already before by but anyway, it also follows from here. I mean, because this, I mean, you need a little bit of argument to pass from one to another, but in principle, anything map finite to AG will work. Okay. Now, let me give some ideas of the proof of By the way, is this property I refer as the hyperbolicity of AG. Okay. So here proof. Right. So so let me pick the following setup. The first one is I assume AG has a gamma L level for, let's see, some L not equal to P and odd. So meaning I'm considering basically so the moduli of abelian varieties with a trivialization of its L torsion for some L odd, not the same as P. The second is I assume, let's see, AG has so-called maximal parahoric level. At P. Basically, here I'm considering some polarized moduli polarized abelian variety, but I want the polarization has kernel is given by some P torsion approach. Okay, the kernel is some degree, some P to some power, but it's all containing the P torsion. These two are basically actually you can basically reduce the general situation to this, because I said that you can sort of move between finite morphisms. So this is not serious. The third assumption, let me assume is S is actually just a point. I just want to deal with the case of extension from the punctured disk to disk. So for general S, it's actually there's some a little bit more. You need a little bit more arguments. So this is just for simplicity. But one could deal with general situation, but a little bit requires some extra argument. So now let me try to. I should just erase here. Okay, fine. So should I do that? So the first thing, proposition 1. So let F now be just a map from the punctured disk to an identification of this moduli of abelian variety defined over the F as in the theorem. Then the abelian rank of X star of A is, maybe here I write the universal, is constant. Or let's say classic points. In this punctured disk. What does this mean? Abelian. So this is a moduli of abelian varieties. So I have some universal abelian variety over it. So X classical point is basically some point given by some finite extension of F. So I can pull back this abelian variety, and then it may or may not have a good reduction. I take it, but anyway, I can take the Néron model, and the Néron model. There's a part that is toric part, and maybe some part is like a quotient, which is abelian variety. So the abelian rank is just look at the dimension of the quotient. So I don't want to write it down because it's okay. So
you take the semi-stable neural after an extension, right?
Yes, you can. You can always pass to some.
Anyway, you have some levels, so it's probably.
Yeah, so because when I have a level. L level. So yeah, this simplifies several things. So this is something I hope I will see more later on. So, but because this is sort of something which allows us to pass from the interior part, which we did before, to the whole part. So maybe before going to the second statement, let me just give you an idea of what does this really mean before going to. I hope I have time. Yeah. So the idea is, well, for me, a fundamental difference between p-adic geometry and the complex geometries. In the p-adic geometry, you have this some extra point living over fp. So you sort of, if you have a map over qp, you always have some reduction of p after you pass to a proper, like let's say, integral model. So suppose you have a punctured disk mapped to this AG, and suppose it extends. If you believe the theorem, if it extends to the map of the disk to AG star, then you can take an appropriate integral model. Let's see. Then this particular origin, this point, will have some reduction to the integral model. So let's see some integral model. In fact, in this case, this minimal compactification has a canonical extension to ZP. This is like there's a theory of compactification of arithmetic compactification of Shimura varieties. So this has canonical extension to ZP, and then you can look at the this point where it goes along to the boundary, right? Or to where it goes. For example, if this point goes into the interior, meaning this abelian variety has good reduction, then over some small neighborhood of it, all this should just go to the residual disk of that point. So all of them should have good reduction. If this point goes to some boundary, meaning it has some back reduction, but you can read the abelian rank from the which boundary strata it goes. But no matter which boundary strata it goes, over a small disk, those points will all go to that boundary strata, and then they will should have the same abelian rank. Then the point of this proposition is that actually you don't need to shrink your disk. Actually, it's as soon as has one point has reduction go to some boundary, then the whole thing will actually land in this equivalent neighborhood of that boundary strata.
And delta was within this?
Delta is closed disk.
Closed.
Yeah. Well, it doesn't really matter because you can write the closed as a union of open as a union of closed. Let's do closed.
No, but I mean it matters for this.
Yeah. Let's do closed. Let's make everything to close disk. Yes. Okay, so I hope to say a little bit more later about this. I give you a little bit flavor why this statement. There should be something similar, the statement of this kind. Okay, because there's a really extra point.
Does this depend on like this precise level structures chose?
As soon as you have this such level, yeah.
I'm a little worried because there are like these modular curves which have genus 0, right? Like if you're trying to make a counterexample to your proposition, you might want to choose like something with genus 0, so you have big disks inside.
But you have a genus 0, but you need to compactify over a bunch of points.
I agree, but the thing that your disk is a closed disk.
This disk is a.
If it's inside, I can make it slightly bigger, but still closed, and it still won't be the cusp, right? Because the cusp is like some fixed distance away or something. Anyway, I don't like this.
I don't. I mean, there's a proof, but. All right.
Excuse me.
Yes.
Can I ask about the rank here? I'm not sure I understood. The rank here, could it be your abelian variety has a multiplicity on all the components of the multiple reduction?
It could have multiplicity.
Your rank would be 0, right?
The rank could be 0, yeah.
As it's accepted.
It's accepted.
But then here your argument assumes that the rank is not 0.
What is not?
Or not the argument, but you were talking.
Yeah, but it could go to, there's actually a boundary strata which is point, like the classifying, those cusp. Those are like rank 0.
Okay.
Could have a reduction, yes.
But I mean, can I ask, and then I stop, could you have a normal crossing model which is regular, but then the special fibers, the mod P reduction, has higher multiplicities on all components?
On all components.
Then, so then we know the semi-stable reduction exists, but your rank is 0, and then you don't have any of those boundary cusps.
All higher, that's I don't know. I'm not sure.
Is it just, but I think you're right to say in that case the rank would be 0.
Yeah, you could do.
Okay.
Yeah, right. By the way, I should also mention as other model for this theorem. For if S as well as S is not empty, this is only true for minimal compactification. Couldn't be true for other integral model. Not other compactification. For S is point, actually, we argument reduces. Actually, need to somehow goes to semi, this Pareto compactification, where you have a semi normal parsing boundary. Okay. The second proposition, which is somehow this theorem, the first proposition says this disk will the reduction will have go to like a different neighborhood of certain boundary strata of AG star, but the minimum compactification has a property that all the strata is basically AG prime for some G prime less than or equal to G. So there's some argument involves the geometry of the compactification. But anyway, once you have proposition 1, it's not gonna far to deduce the whole theorem from a good reduction locus. Namely, let F to be a map from the punctured disk to the rigid generic fiber of the formal completion of this abelian varieties of AG over ZP, which means basically you are considering the locus with where the abelian variety has good reductions. Your map, your analytic map over F, then F extends to a map from the disk. So it's already extends here. Another way to say this, if you have a family of abelian variety or pluralized abelioid over punctured disk, it will, if at the say one point it has a good reduction, then the whole family actually extends through the disk. It's a kind of so now, how to prove this kind of proposition 2 is actually, again, you keep this picture in mind that if you have such an extension, then the origin, the center of this puncture of the disk, this missing point must go to somewhere, like its reduction mod P must land in some particular point in, let's say, mod P fiber of this, and then a small disk would actually should map to some residual disk of that point. So now, in the same spirit, but sort of some different, different argument, we can do the third part. So for that, I need to introduce the following. We call a little bit about the Rupple-Zink space. So let's take three. This let F you map from the punctured disk to this rigid generic fiber of AG as above. Then there exists a lifting of this map originally from the map from the punctured disk to some I call RZ B X. This is certain where just write Z. It's X is certain Rupple-Zink space. Write the bar. Which classifying the following thing. You firstly one can define as a formal scheme over like a maximum ramified completion of maximum ramified extension of DP, and then take this rigid generic fiber. And for this reason, that's the reason I want to take some parahoric level, because somehow this is really actually it's already used somehow here integral model. But anyway, so it's classifying the following thing. It's a function in the category of p-nilpotent VP algebras. The following triple lambda iota, where A is A lambda is some polarized abelian variety over let's say R, and iota is a quasi-isogeny of this right with some given one. So this one is some like the prescribed given one abelian variety. This is so it turns out that this this is a representable formal scheme. Over the P brief, and then you can take the rigid generic fiber. It turns out what happens is this is sort of some uniformization of part of this abelian AG. So this is the story is a little complex, different in this p-adic situation of and this complex situation. In the complex situation, we know this the Shimura D mod gamma is always uniformized by some D, but here in this story, it's actually in general it's only uniformized part of the part of this rigid analytic variety. Actually, this map factors through some quotient, and then this is kind of some turbulent neighborhood of some closed subscheme inside it. So this is sort of some properties lifting some map to some kind of its covering map. Which in particular says that if you have on this puncture, the content of this proposition says that if you if a family of abelian varieties over this punctured disk, you take 2 points, then their reduction modulo, any power of the prime actually are isogynous to each other. Okay, so this disk can't be really go very large in this, and lands in some isogeny class.
What is this X bar in the notation?
XR is X bar is actually, as I said, if you think about it, if there's such extension, then this center will have some reduction to some points on the spatial fiber. Actually, you can take you can think about this X bar is like this reduction. But actually, in practice, what you do is if you have such map, you take some any kind of integral model, take any point here and take its spatialization reduction that could serve as X bar. Right. So the last part is the following theorem, which is this Borel's extension properties actually holds for RZ space already. Map from the punctured disk is the link space. If you take the rigid generic fiber, extends to map across the disk. So for this kind of this space, it has this extension properties magically. So I hope at least proposition 3 and this let's call it this theorem 4, they together should implies proposition 2. That should be clear. And once you have proposition 2 and proposition 1, then plus some need a little bit of argument, and then you get the main theorem. So is that okay? So now I have a sort of time always goes very fast. Less than 10 minutes, so I probably could talk. I already give you a little bit hint of idea of 1, although I want to talk more, but this is a p-adic conference. Actually, 1 and 3 uses some algebraic methods and something specialized to abelian varieties. Part 4 is more like this p-adic thing. So maybe I still take some time first to talk about proposition 4 and hopefully get to what you have. So what is the idea? The idea here is I have basically what I'm saying is basically here I have a family of p-divisible group or like some family of abelian variety. Let's see over it together with isogeny to some fixed one. So and then I want to extend this abelian variety across this missing point. That's a little bit hard to extend directly. But somehow we could first extend its cohomology through the function. Some kind of the cohomology theory, it's like some, let's say, p-adic Tate module, or it's some other like some other data across the boundary. So this uses the following some kind of some basic version of some kind of Riemann-Hilbert correspondence, which is you have the following ZP et al. drum local system on the punctured disk. So such data actually already let's say actually it will come from this family of p-adic module of this family of abelian varieties. But under some like kind of comparison, it will correspond to the drum cohomology, which is vector bundle with a connection and the filtration satisfying Griffith's transversality. But because we are in this rubber zinc space situation, all the abelian varieties are isogenous to a given one. So this family of drum cohomology actually is canonically trivialized. It's basically the Dieudonné rational Dieudonné module of that particular one. But in any case, so the idea is now you want to sort of extend all this local system and the vector bundle with connections to first to this disk. So this uses the following thing. So there's not the equivalence, but there's actually functor. So the physical functor is etal drum local system on here to vector bundle with log connection on the disk and the filtration, decreasing filtration, satisfying Griffith's transversality. And plus like the if it's a log connection, then you can talk about the residue, and the residue exponent of residue has like has exponent rational numbers in 0 and 1. So this was proved some time ago in joint work with Galen Liu. And okay, so how do we apply this? Well, we already know this vector bundle is connect. This vector bundle is canonically trivialized. The connection is also trivialized. So the canonical extension is nothing but the trivial extension. But then what's really non-trivial is extend the filtration. The filtration can also be extended to the to 0 to get the filtration. And that's in picture, what you have is what really is the following thing is you have your punctured disk mapped to some RZ space, which have this modular interpretation, but it maps to the flag variety because as I said, the drum cohomology canonically trivialized. You just remember the Hodge filtration. But now I'm saying that this filtration can be canonically already extend here. That's a whole point. Meaning this map actually has no essential singularity. It extends across. And then you will see this extra point and will go to some point here. Then you can check actually using some result of code. It's actually first of all lands inside the so-called the admissible locus. So that means the extended ZP representation is actually a crystalline representation. So it's lands in the image of here, and then you can sort of lifting this map from the disk to RZ space, because this is basically classifying. You know, there's over this admissible locus, there's a universal QP local system, and this is classifying basically ZP lattice inside it. But this is actually, I didn't see that, but this ZP local system could also extend and give you some kind of lattice. So that is already gives some idea of why the last part is. Okay, so maybe in 1 minute, let me just give one idea, a little bit flavor to prove proposition 1. So actually this, I can always write this punctured disk. As the idea is I can always write my punctured disk as a union of annuli. And what I need to do is actually to check this this abelian rank is constant on each annul. So the easiest situation is I just consider this single annuli actually the inner radius and the outer radius is the same. So so this punctured disk is written union of let's say some annul, some R1. The particular case that is easy is the following. It's this when the annuli is just 1, 1. Okay, let's see. Suppose what I want to prove. I suppose I want to prove if it has a point with maximal abelian rank. I want to show it has a maximal abelian rank everywhere. But according to Gorthendieck, we can test it by just looking at the L-adic Tate module, how the inertia acts on the L-adic Tate module. But the whole point is the pi1, and as I trivialize the first L torsion, the monodromy group will prime to P. So I can just look at the prime to P L-adic fundamental group. I have a local system on here coming from the L-adic local. But then the first fact is this actually the fundamental group, prime to P fundamental group of this annuli is the same as the algebraic fundamental group of GM. So this local system comes from some local system GM. And now I have a whole point is over here, if I have a point X, I have this pi1 of X mapped to it. I claim as soon as this representation composed, I have this composed representation to some GL, some LX. Okay, that Tate module. As soon as this representation is unramified, the composed representation is trivial on the inertia. Let's see. Actually, it extends factors to the representation of pi1 of GMO mapped to it. The reason is basically this point when it lands on this thing annuli, it extends to an O point. Using this commutative diagram, actually the kernel of this will be mapped surjective from the kernel of this. So as soon as this map factors through here, this map will factor through here. That shows that it actually extends pullback for locus and GMO. Means it will be unramified everywhere. But this argument, I should say, doesn't hold when if your point is some inside. Actually, this quotient, this inertia and some geometric fundamental group doesn't really match. You need some something specific to abelian varieties. Okay, I think I should stop here.
Thank you. Are there any questions?
In this proposition 2, on the right, you have something which is quasi-compact.
Quasi-compact.
So do you have examples of like maps from D star to something quasi-compact which don't extend?
Which don't extend.
So I mean, in other words, I'm asking, is this like some more general, maybe some more general special cases, some more general?
But I mean, if it's quasi-compact, or map to some quasi-compact, yeah. But you can even just map to P1, map to A1 inside the P1.
Okay.
Yeah. It has essential singularity.
But A1 is not good.
Yeah, but it's inside P1 is. I don't know what do you mean. The image is quasi-compact, or it's just mapped to something quasi-compact.
Also, does this p-adic hyperbolicity holding positive characteristic non-Euclidean geometry?
In what? Positive.
In positive characteristic non-Euclidean?
Uh, so I don't know. You mean replace f if f is not equal characteristic now? Yeah. I don't know. Certainly the method doesn't work. Some p-adic method. This part probably okay for this. Like,
I'm sort of guessing that you might be using something about local systems on a punctured disk, also about their wild ramifications. I'm not sure, but
yeah, maybe I don't know.
other questions?
Is it possible to have the theorem over CP?
Over CP, yeah, I hope so, but there are several places actually use this discrete. I can't remember some. I mean, they was used in many places, but somehow, because when we take somehow when it, for example, when we talk about like the nice integral model of this analogue, we want to f is discrete value field, but those part maybe should be extendable, I think. But there's also this part. I don't know what's the status. Can one do this just over CP? If that's possible, then something here can also be extended. Maybe there's that. But certainly, I think it should be true over CP.
Sorry, the same spirit, but easier, hopefully. What about the complex, like C power series T?
So power series T, I think there are some work before. I can't remember, but there are some work before to talk about those stuff. This kind of C power series T.
I mean, like the statement is true there.
I think so. Yeah, there's some different some statement I need to check.
Okay, thank you again.